Okay, kids, let's get rolling here. So we're just going to jump into this one. We've spent some time introducing logs, and we've done a little bit of graphing with logs. Now we're going to look at the algebra a little bit more here. So 5.3, Logarithm Laws. So basically, there's not a whole heck of a lot to say here. What we'll do is we'll be looking at a few laws of logarithms, and then we're going to spend our time working through some examples. So let's have a look here. Just like the exponent laws that exist, there's also logarithm laws. So they're very, very similar. Side by side, we can see what they are. I'm going to zoom in a little bit here so it's easier to see. But what we have is we've got three laws, and we've got the product, quotient, and power law. So first of all, on the right side, we've got the exponent laws, and this is just a reminder for you. This is nothing new. When you have two similar bases with different exponents, when you multiply them together, the exponents add up, and then when you divide the powers, you subtract the exponents, and then of course when you raise a power to an exponent, you multiply them together. What this looks like for logarithms is something kind of similar, although it's not going to look exactly the same. So here, the log of two things multiplied together is equal to the log of x plus the log of y. So this is kind of similar in the sense that when you think about logarithms as exponents, well, we've got like an x times a y on the left side here, which kind of corresponds with this, and then we've got an x plus a y on the right side there, where we've got log x plus log y. So if we're saying logs are exponents, which is what they are, right? Logs are the exponent calculators. Then we can kind of say, well, this here is kind of like x being in the exponent position and y being in the exponent position, so it's kind of like that. Anyway, so we're going to do a lot of hand-waving analogies here to show how this and this are kind of the same thing, but we'll also show it with algebra, and for the most part, 90% of you will probably just be happy trusting me on this. So let's just look at the other rules here. So what we've got is we've got the product law. When you take the log of things that are multiplied, you can split them up into a sum of logarithms. The quotient law, when you take the log of things that are divided, you can split it up into a difference of logarithms. And then the power law. This is the really interesting one. When we've got an exponent, like we're taking the log of x to the k, we're actually allowed to do something really, really nifty. This k gets to come out in front, and it becomes a coefficient. That's going to be humongous later on when we're solving equations, because this is the one single thing in all of math that allows us to get rid of exponents and bring them down into a more useful position. All right, so a little proof here. Now, most people, if you're like me, you're sitting there going, I don't really care about the proof, but you should have a look at it. It's worth seeing, even if you don't grab all of it right away. It's worth having a look just to see that the stuff isn't totally made up and you can actually work it all out. Okay, so if you wanted to prove the product law, and the other laws will have similar proofs, I'm just not going to do them all. But the product law, so you can actually start by turning the log base whatever of x into m, and then log base, same thing, y equals n. Putting that in exponential form, you can write that as b to the power of m equals x, and b to the power of n equals y. So using the well understood rule, when you multiply two things together, like x times y, that's like multiplying b to the m times b to the n, and then that we all know you add the exponents because that's been proven a long time ago, so we'll just take that as something that we know. Now the neat thing here is if you take this and you take this and you rewrite this back into log form, it might take a second just for practice to envision how this works, but remember you're going log base b of whatever equals to the exponent. So if m plus n was the exponent, then it would equal that, and of course going back here saying that m was this and n was this means we can replace m and n with those things. If you followed all that 100%, good for you. If you just sort of glazed over and said, okay, whatever, I trust that it works, that's fine too. Just a little bit of, not a proof, but just an example of how this can work. Like let's say we want to do log of 1,000. what this is saying is I could split up log of 1,000 into log of, let's say, 10 times 100. And then the product law is saying, because it's log of 10 times 100, I can split this up into log of 10 plus log of 100. And of course, log of 1,000 is equal to 3, log of 10 is equal to 1, and log of 100 is equal to 2, and last time I checked, 3 is equal to 1 plus 2. So that's a little simple numerical example that can just sort of illustrate this in more concrete terms. Okay, so example 1 is to use logarithm laws to write as a single logarithm. So this is a pretty standard textbook question. This is not something you're going to do on a daily basis when you're shopping for bananas, but who knows, maybe. Okay, so what we do here, and now this question is picked very specifically because we've got a minus sign and we've got a plus sign, and I wanted to illustrate something that people screw up quite often. I'm going to show you the right way and the wrong way to do this. So first of all, the right way to do this, because this is the one that'll stick in your head, is to write this as log 40, but because we're subtracting log 4, this gets to be divided. So when we just go back up and remind ourselves here, if we've got like log of something minus log of something else, we can actually write it as the log of those two arguments divided. So log of 40 minus log of 4 will actually be log of 40 over 4. Okay, so I'm just dealing with these two guys here. Okay, so that's log of 40 divided by 4. Now dealing with this log of 5 over here, because it's a plus sign, we're going to multiply, and again, this is all in one big argument. We're going to multiply it by a 5. This is the correct way of doing it, so everything I'm saying is all good and legit. So this is actually going to turn into log of 40 divided by 4 is 10. 10 times 5 would be 50. And that's it. We're not asked to evaluate it. We're just writing as a single logarithm. Okay, so that's just a little bit of use of the quotient law here to deal with the first two, and then the product law to deal with the next guy. One thing that could be done, and I've seen this a lot, so I'll just show you, this would be the wrong way, is to think of this as log of 4 plus log of 5, and turn that into log of 4 times 5, which is log 20, and then to go log of 40 and then divide it by 20 and say that's like log of 2. That would be wrong. Don't do it that way, and I'm going to actually erase this. Just keep in mind that pluses and minuses are the same order of operations in BEDMAS, so the way that we do it here is we always go from left to right. So if you've got a string of a bunch of terms added and subtracted together, you always start at left and work your way to the right. So you're going to go log of 40 minus log 4, which is divided by, and then you're going to be multiplying by 5 later on. What I did in the wrong method is I kind of snuck brackets in, and I did those two first, so just don't do that. Okay, and I'm going to erase this, because when someone's looking at this later, they're going to go, why is it a right way, not a wrong way? Okay. This one here is a pretty straightforward one as well. This has log x plus 2 log blah, blah, blah. Okay, so the one thing, the main reason why I chose this example is we had some variables instead of numbers, but that doesn't really change the rules. The big thing here is I wanted to address what you do when you have things like coefficients. Even stuff like square roots, we're going to clean those up a little bit. Well, maybe not necessarily in this example, actually. I take it back, but we definitely got to deal with that too. When you look up at our rules here, you'll notice all the rules, log is always by itself. There's never a coefficient out in front. So to use the log laws, all of them, we have to get rid of coefficients. And the way that we're going to get rid of coefficients here is we've got to first take this 2 and we've got to bring it up into the exponent position, so that now I've got log of x, and then I'm going to be adding log of y squared. And then this one can say it's log of root 2. You'll see later, sometimes we'll deal with the root 2, but not for this one, because we actually want the coefficient in front of all the logs to be equal to 1. Let's just write a tiny little note. Must make all coefficients in front of log equal to 1. to use the laws. Okay, so this is really important. You cannot use the laws otherwise. So what we're going to do here is now once we've got all the coefficients equal to 1, which we do, we can now simply apply the rules. So this can be log, big fat brackets here. You've got log x plus log y squared. So that's going to be x times y squared. Then we've got a minus log root 2, and that root 2 will then be the division part here. Okay, so whenever things are added, they go on top. Whenever things are subtracted, they go on the bottom. And some people are even happy enough to just say everything that has a plus sign, like log x and log y squared, everything that has a plus sign goes on top. Everything that has a minus sign goes on the bottom. You could think of it that way if you really wanted to. Okay, this one here, this is a bit of a different style of question. This one says write as a single logarithm, but we don't have two logs, so we can't combine them. Guess what, though? You can always turn things into logs. This is equal to log, and now we have to have the same base as well. So it has to be log base 2, and it's log base 2 of what? So this is where you sit there and you think about this, maybe somewhere off on the side, or maybe it's obvious, but somewhere off on the side you think, okay, well, log base 2 of question mark is equal to 3. What is the question mark? So the question mark is 2 to the power of 3 equals 8, so log base 2 of 8 is equal to 3. So what this is going to be is we're going to write this as log base 2 of 8 plus log base 2 of 3. And now, because they're the same logs, they don't have any coefficients on the front, I can combine them into the same, into one logarithm, where I go 8 times 3. And then this will be log base 2 of 24. Don't forget to include the base. If it's not base 10, you have to write that little number down. It's very common for people to forget that. Okay, and then this one here. This one looks really complicated, but it's really, really, really not. Okay, so if you're going to deal with this, you might already know sort of the general drill. We have numbers out in front, coefficients, we got to get rid of those. So the way that we're going to get rid of the 3 and the 2 and this one here and this one here, we've got to get rid of all of them. So we'll simply do that by bringing it all up into the exponent position. So when you're dealing with numbers like 3, you're going to bring that up and make it 3 cubed. When you're dealing with stuff like this, remember dividing by 2 is the same as multiplying by half. So I could think of this as 1/2 times 3 log 5. And then what I'm going to do is when I bring that 1/2 in, it's actually going to come in as 3 over 2. So let's actually write that out. This is the same, this is the same as, I prefer to rewrite it as 3 over 2 multiplied by log 5. This is 2 log 3, and then this one is 1 over 2 log 9. Bringing all of this, all these coefficients up, so this becomes log base 5 to the power of 3 over 2. This becomes log base 3 to the power of 2, and then this becomes log base 9 to the power of 1/2. Just cleaning it up a bit more. So 5 to the 3 over 2, that's 5 cubed, which is 125, and then this becomes root 125, I guess. This one will become log 3 squared, which is 9, and then this one is the square root of 9, which is 3. Altogether now, we can do one single log, big fat brackets here. We've got root 125 multiplied by 9 divided by 3. This, of course, can get cleaned up a little bit more, so that's log. Let's see, the 3 and the 9 can cancel out. Put the 3 up there. So this is 3 times root 125, and of course, that can be simplified down because root 125 is 5 root 5, so this can become log of, what's that, 15 root 5, I guess? My thought bubble up here is root 125 equals 5 root 5. Okay. Here's another one. This is similar, but just a little bit different here. Write each expression in terms of the individual logarithms, log x, log y. So what we're kind of doing is kind of doing the opposite here, where instead of combining something into one log, we're splitting it up. And we're saying just in terms of these things. So our steps here, because I've got log of x squared times y, I can split this up into log x squared plus log of y. This isn't exactly in terms of log x and log y. We're not supposed to have log x squared, we're supposed to have log x. So the way that we do this is we're going to write it by bringing the 2 out front. This will be 2 log x plus log y. Once we've got it looking like this, life's good. Put a box around it, everyone's happy. Okay, so we've got 2 of this thing and 1 of this thing. Okay, passive viewers, if you haven't done anything, maybe pause the video and give this one a try. I'll trust that you did because you're all such diligent students. So let's have a look here. So we've got log of, now we've got 2x on top, we've got 3y and root z on the bottom. So the way that we're going to deal with this guy here is stuff on top is going to be a positive log term, so log 2x. We're going to go subtract log. Now I could split it up into like 3 and then log y and then log root z, or I could just say something like log of 3y here, and I could split it up as log root z over here. It doesn't super duper matter at this point, although it, oopsie doodles, we might actually find, I think how I sound like Ned Flanders sometimes. Whoopsie doodles. Okay, so anyway, it doesn't really super matter at this point, but I'm kind of imagining this to be like one piece, and this is another piece, and this is another piece. So that's sort of how I'm splitting it up. Of course, we do have to split it up into x's and y's. So what I'm going to wind up doing here is I'm going to have to actually split this up into something like log of, maybe I'll put brackets around here to make sure I'm doing this correct. Log of 2x can get split up into log 2 plus log x. I'll subtract log of 3 times y can get split up into log of 3 plus log of y. And then this log of root z, you'd actually want to write that as log of z to the 1/2. And then this can come forward the power rule. So finally, I can kind of put this all together, and I can write this in terms of x's and y's and z's. We will have a couple log 2's and log 3's, but that's okay. I don't think there's much we can actually do about that. So what we're going to have here is, let's just put it all together without brackets, clean it all up. So we'll have log 2 plus log x minus log 3 minus log y, don't forget the brackets, and then minus 1/2 of log z. A similar kind of question can be asked where they actually tell you what log x, log y, and log z are. So they'll like associate a number with them, like maybe log x is equal to 5, log y is equal to 2 or something, and then they'll ask you to calculate them. So just be aware of that. That's why we're splitting it up in this way, so that we've got log x by itself and log y and log z by itself. And in fact, I actually think that's one of the upcoming examples. So here we go. So this is a similar kind of thing. Determine the value of each statement, and you're given log a is equal to 5 and log b is equal to -1. Now I'm going to go ahead and tell you that when people see this, they're going to be so tempted to figure out what is a and what is b, and you absolutely 100% can do that. If you know log a is equal to 5, you can always turn it into, what's that, base 10 to the power 5 is equal to a, and base 10 to the power of -1 is equal to b. But you know what? You don't even have to do that. What we're going to do is we're going to skip that step, and we're just simply going to use a similar technique as we did in the last example. So this is going to become log of, now it's 100 times a squared times b. So this can become log of 100 plus log of a squared plus log of b. Now, if I want to actually evaluate this, I'm going to do nothing with log of 100 because I can actually evaluate that just simply. This one I'm going to bring 2 out front, so it's 2 log a. This is log of b. Don't start thinking you're real clever and say, okay, well, if log a is equal to 5, then log of a squared is like 25 or something like that. No, it's actually not going to work that way. You cannot evaluate log of a squared. You have to bring the 2 out front. Okay, now this thing is pretty simple. Log of 100, remember base 10 is assumed. So that's actually equal to 2. This is 2 times, now we're actually told log A is equal to 5, so this is 2 times 5. And then log B is equal to -1. And just like that. I'm not 100% sure why I switched colors to do this, but it just felt right. So let's just go back to red. And we've got, what's that, 2 plus 10 minus 1, that's 11. Ta-da! Now if you went ahead and you did all the stuff that I said you don't have to do, you could have done the alternative method where you actually work out that 10 to the power of 5 is equal to A, and you could have went 10 to the power of -1 is equal to B, and then you would have had log of 100 A squared times B. You actually could have worked it out this way, where it would have been 100 multiplied by, what's that, 10 to the 5th squared, and then B is 10 to the -1. The reason I'm doing this is just simply to reinforce the fact that we're just dealing with exponents, and there's a lot of common sense ways you can solve these things. So let's see, this would be, basically that'd be 10 squared times 10 to the 10 times 10 to the -1, and this would have wound up being the log, and then you could use your exponent rules, right? Add up the exponents, this would be 10 to the 11. And of course, the log base 10 of 10 to the 11 would be 11. I think that's a lot more work to do it that way, but you can go ahead if you really wanted to. And it's nice that it works both methods. Okay, next one. Pretty similar here. Again, I would recommend you stop the video and just try it yourself. And then I'll just go through it pretty quick. So this will become log. Now we've got B over root A, so this is going to become log B minus log of root A. Then we'll have plus log of 1. Using a similar technique where we've got to get A by itself, we'll think of this as log A to the 1/2. Then we've got log 1 here. Now if you're sitting there shouting at the screen, but log 1 is just equal to 0, you're absolutely right. So let's stop writing that. If you need a refresher, why is log 1 equal to 0? Because 10 to the power of 0 is equal to 1. Okay, so this is equal to log B minus 1/2 log A plus 0. Now we know that log B is equal to -1. And we know that log A is equal to 5, because that's what was defined earlier on. So now we can write this simply as -1 minus 5 over 2, which is equal to -7 over 2. Nifty. Okay, oh, here's a fun one. I actually like these word problems because they actually come up a lot. Those of you who are in chemistry, dirty chemistry, you know logarithms actually are used a lot in pH calculations as well. So I decided to pick something a little different. Here's the Richter scale. So we've all heard of the Richter scale, and a lot of us have a pretty decent idea of it, but let's just look at the mathematical formula for it. So the Richter scale is a way of measuring the intensity of an earthquake, so the actual ground shaking, like the amplitude of the waves and all that sort of stuff. But we give it a magnitude, and the magnitude will be m. And we use this equation here. We say the magnitude is equal to the logarithm of the intensity. So the whole point of this is saying that if the intensity is small, then the magnitude is small. But as the intensity gets bigger, the magnitude gets bigger, but it doesn't get bigger as fast. So we're taking log of the intensity. And the reason for this is very simple. The weakest earthquake maybe has an intensity of 1, and the strongest has an intensity of like 1 trillion. We don't want to say magnitude 1 and magnitude 1 trillion because it kind of makes no sense. No one's going to understand that. So you might even know that earthquakes actually tend to go from 0 to 10 roughly, although there is no theoretical, there's no practical limit to what the magnitude could be, but there is a theoretical limit, because if the magnitude was big enough, the earth would actually crack from it. So some people will say you can't have an earthquake bigger than 10. It is possible, but once you start to get up there, you do start to run into the risk of, continents splitting apart. That would be bad. Anyway, 0 to 10 is kind of the rough scale for the range of magnitudes. Anyway, let's do the question. So 2 earthquakes are recorded. Earthquake A has a magnitude of 4.7, while earthquake B has a magnitude of 6.1. How many times more intense is B than A? So the way that you would go about doing this is, first of all, this does not give you enough information here. And it's not as simple as, those of you who've taken physics and maybe even chemistry, you can put a little change in quantity, like a little delta. You can't stick a delta here and here. That doesn't work either. So what we're going to do is we're going to say the magnitude of earthquake A would be log of the intensity of A, and the magnitude of earthquake B would be equal to log of the, that's a terrible G, log of the intensity of earthquake B. So what we can do is, if we know that earthquake B and earthquake A, so I'm going to call this MB and MA, we can compare the two by subtracting them. So we can find the difference in the magnitude. So we're going to turn this into one equation here. We're going to go MB minus MA, so weird M, and then we're actually going to subtract. Okay, so we've got MB is equal to log of IB, the intensity, minus log of the intensity of A. Who else is excited for allergy season starting? You might even hear it in my voice, a little more nasal than normal. Okay, so what we have here is we've got MB has a magnitude of 6.1, and we've got MA, which is a magnitude of 4.7. So we go log of the intensity of B. Now, do we know the intensity? No, we don't. So the best we can do is this. Now, the question is saying, how many times more intense is earthquake B compared to A? So how many times more? This would be great if we could express it as a ratio, like what is IB over IA? So how can we go from what we have here to this ratio? And the answer is really simple. If you notice, we've got a bit of a log law situation. So the difference in magnitudes is 6.1 minus 4.7, so that's 1.4. And because we've got log of IB minus log of IA, this actually is a situation where we can write this as log of, and we'll use the quotient law to write it as log of IB over IA. So using that little clever bit of mathematics, we now have a ratio, and we just have to solve for this. So the way that we're going to solve for this, the easiest way, is to rewrite this in exponential form. So what we're going to do is we're going to think about, how do I write this in exponential form? So remember, this is log base 10, so the base of, is 10. Logs are equal to the exponent, so 1.4 is the exponent. And then IB over IA is what's left over, so that goes on this side over here. So the ratio of these two, which is like how many times stronger or more intense is earthquake B than A, is 10 to the 1.4. And just to work this out, we'll go to calculator, and we'll just go, okay, 10 to the 1.4, and I think my calculator likes it when I type that in first. There we go. So what this tells us is we've got an answer of 25.1. Okay, so the ratio of IB over IA is equal to 25.1 approximately, okay? So what that says is, therefore, and because of the word problem, it's nice to say this in a word sentence, earthquake B is approximately 25 times more intense than A. Cool. Okay, so then you just take a sec and you make sense of this. Now the sort of common sense check is every time the magnitude goes up by 1, the intensity is going to go up by 10. And I hope that makes some sense to you, because we're taking the log of it. So if the magnitude goes up by 1, the intensity goes up by 10, and that's because the log of 10 is equal to 1. If the magnitude went up by 2, the intensity would have to go up by 100, because the log of 100 is 2, and so on. So maybe this explains also why when you hear someone experiences a magnitude of 5, it's kind of bad, but not that bad. And then when they get a 6, it doesn't sound that much worse, but it's 10 times worse. And a 7 is 100 times worse than a 5, and an 8 is 1,000 times worse. And the most intense earthquakes ever recorded, I believe, were somewhere around like 9 point something. So that's where you're getting to like thousands of times more intense than a 5. And a 5 is not great, but it's not that bad. 9s are devastating, and a 10, like I said, that's humongous. So it grows quite quickly. The intensity actually grows exponentially as the magnitude goes up. Okay. Anyway, that's the main idea. Most of these types of word problems, there's a few in the homework. They're all very similar. There's ones with PHs and all that. The approach you're generally going to take to determine how much bigger, how much more acidic or whatever, is it going to be a similar approach to what I did here. So I hope that's helpful, and we'll see you on the next one. Enjoy logging, kids. Oh, also, don't forget to log off the internet once in a while.